Well, hello, people out there. Welcome to part two of structural equation models and overview. I want to remind you again that this is made possible through a National Science Foundation and their sponsorship of the SAMSI program that is based at UNC, Duke, and North Carolina State. I also want to thank Ilya, who is helping with the recording. And just a reminder too, that if you would like to ask a question, you can indicate that on the chat. Ilya will be monitoring that. And if you just want to say, I'd like to ask a question, we'll have a point at which we'll take a break for questions. Or if you want to type in the question and it's something for clarification of what I've just gone over, Ilya will just get my attention and I'll be happy to do that at that time. So by way of refresher of what we covered, this is the outline of what the whole overview is about. And we were able to get through these first three Roman numerals here. And a lot of it was really just trying to give you a feel for what these structural equation models are like, what some of their capabilities are. Now today we're going to get into a little bit more of the details, and then we're going to look at one way that we can represent the model, and then talk about the steps you have to go through in order to use structural equation models. And throughout going through these steps, we'll be looking at a series of examples to try to make them more concrete. Next will come the major steps. The software. We'll be looking at some of the software that you can use for this. And then we'll have an empirical example, and I'll show you what the code looks like in two packages. One is Lavon, it's an R package, and the second is Mifsum, which is another R package. I chose both of these because they are R packages and therefore they are free, and you would be able to download them and use them yourself. Have a little bit of the conclusions. The references will be given in a final section. And depending on time, I'm not sure if we'll have enough time or not, but there is a supplemental slide on this that shows the M+ code, another popular structural equation modeling package for this same empirical example. So without further delay, let's go to the model and notation. Just as a reminder, structural equation models give us the capability of estimating models where we have theoretical variables, which we're going to refer to as the latent variables, and we have observed variables in our data set. And we can incorporate both of them, which gives us the ability to control for measurement error, to have a multi-equation system that we can look at, where latent variables are related to each other or related to observed variables. So the model and the notation is going to reflect those capabilities. To get started, let's distinguish between three types of variables. The first type of variable, and we've already seen this in some of the examples, this Z, which we've used to represent observed variables. These are variables that are actually in the data set that you're analyzing. The second type of variables are going to be called latent variables. These are the variables that we don't have perfect measures of, but they are in essence what our hypothesis is relating. So if we want to look at something like how discrimination affects income, well, we may have some indicators of discrimination in our data set, but none of those indicators are going to be even close to a perfect measure of discrimination. The latent variable in this hypothetical example would be discrimination. This is what is of theoretical interest. The observed variables, perhaps a scale or several items that are measuring discrimination, these would be the observed variables, the Z. So those are two different types of variables. One's in our data set, one's in our theory. the Z in the data set, the L in our theory. And then the third type of primary variable we're going to look at are errors or disturbances. And I'll use those terms interchangeably, error or disturbance. For each variable that's in our analysis, the error term or the disturbance contains all the other variables that are influencing that latent or that observed variable, but are not included in the model. So it's just a collection of every other force that's acting on that variable. If you wanted to, you could consider this a type of latent variable, but it's a little bit different than the L here because the L generally has some substantive meaning assigned to it, whereas the error is just this collection of many other causes of a given variable. Now, focusing on the observed variables, the Z's, and the latent variables, the L's, these fall into two important categories. One category are exogenous variables. The exogenous variables are not the object of our explanation when we build our model. These are not what we're trying to explain. These are variables that are important to have as part of our system, but we're not trying to explain the variance in them. They're taken as given. Something else explains them. Our task is not to try to understand that. Typically, these exogenous variables correlate with each other, and we connect them with a curved two-headed arrow, which, if you were with me last week, we showed you that symbol. The curved two-headed arrow just says, allow these things to be associated with each other. My model's not explaining why, but I'm recognizing that in the observational world, these can covary with each other. We also assume that if we look at those errors of the endogenous variables, and the endogenous variables I'll be defining in a moment, but if we look at the error terms of the endogenous variables, we assume those omitted variables that are explaining these endogenous variables are uncorrelated with the exogenous variables. And this is the definition of endogenous variables as we'll be using it. These are the variables where we're trying to explain them in our system. You know, these are some key outcome variables that we have other variables in our model that we believe are influencing them. And so they are called endogenous within the system. They appear as a dependent variable in at least one equation. Now, these dependent variables, there are the usual ones that we can think of as substantive variables that we're focusing on explaining, you know, what increases, let's say, social capital or a person's happiness or whatever we're trying to explain. Those are the very common ones we think of as endogenous variables. But as we'll see in this notation, another very broad class of endogenous variables are measures, indicators of these latent variables. They're endogenous because they're dependent variables. They're dependent variables that often depend on the latent variable. So their explanatory variables are latent variables. So indicators in general will be endogenous variables. Now, if we have two endogenous variables and they correlate with each other, quite often the reason they correlate is a common dependence on other variables. Could be other endogenous variables, could be other exogenous variables. And that statement raises another point that a given endogenous variable may be an explanatory variable in one equation, but a dependent variable in another equation. That is in contrast to the exogenous variable, which always appears as an explanatory variable. It never appears as a dependent variable. This is an illustration of a structural equation model, and it has the different types of variables we talked about. And let me go over this to try to explain it. And just as a reminder, ellipses are used to represent latent variables. In this model, we have 5 latent variables of substantive meaning. So we have, this is a representation of very common model in social psychology, also used in population studies, some in sociology, political science, some behavioral intention models, where you're interested in a particular behavior, and you think that one of the primary determinants of that behavior is the intention the person has to engage in that behavior. And then what determines that behavior intention? Well, it's past behavior, the attitude the person has toward that behavior, and the subjective norms. So in this diagram, we have two endogenous variables. We have L1, behavior intentions. Why is it endogenous? Because we've got three other variables that are influencing it. And we have a second latent endogenous variable, behavior at time 2, because it is dependent on behavior intention, L1. The three exogenous variables in this model, exogenous latent variables, are the behavior at time 1, attitude, and subjective norms. These are exogenous because there's nothing in the system that's explaining them, but they are appearing as explanatory variables in the system. I mentioned that for exogenous variables, we often will correlate them. We'll allow them to be associated. That's what these curved two-headed arrows are showing. It's allowing these three exogenous variables to be associated. It's saying, I don't know why behavior time 1, attitude, and subjective norms are associated, but in this model, allow them to be, because this is observational data. Now, another class of endogenous variables are these Z variables. All the Z's here are measures, they're indicators of these different latent variables. So they're endogenous because they depend on the respective latent variables. Z7, 8, and 9, these are measures of behavior at time 1. Z10 through 12, measures of attitude at this point right here. The other aspect of this diagram that I'd like to highlight is you'll notice the first indicator under each of the latent variables has a coefficient of 1. This is to represent the assignment of a scale to the latent variable. When we're dealing with any variable, we have to give it a metric. Regardless of what the latent variable is, there's no inherent metric to it. And if you're not going to assign it some units, we really can't talk about it. So what I'm showing here is that for each of these latent variables, I'm giving it units that are similar to the latent variable. I'm making the latent variable and this Z1 have similar units. I'm saying similar and not the same because this epsilon will make it, the Z1 bounce up and down a little bit, so it's not exactly corresponding to L1. It's on average, if L1 increases 1 unit, Z1 will increase 1 unit. But in any given instance, it'll be a little bit higher, a little bit lower, because we have this disruptive effect of epsilon Z1. That same story could be told for each of the remaining 4 latent variables. So we have then the exogenous and endogenous variables in this diagram. We have the difference between the latent and the observed variables. And just as a reminder, the single-headed straight arrows are indicating the effect of the variable at the base of the arrow on the variable at the head of the arrow, whether it's latent to latent or a latent to an observed variable. And these curved two-headed arrows are indicating association between the variables that are linked by those two-headed arrows. So this is the picture. This is the path diagram. And these are the equations that correspond to the path diagram. As you'll see, as we'll talk about, the path diagram is a picture of a set of simultaneous equations. So it's just another way of representing these equations that some people find much easier to grasp than just looking at a series of equations. But the information that's contained in the path diagram or in these equations is the same. And I could look at that path diagram, just read these off, or I could look at these equations and create a path diagram from it. But here are the two endogenous variables, L1 and L2. L1 is a function of these three exogenous variables in an error term. L2 is just a function of this single one. And then down here, the L3s, these are just a function of a constant, which is actually in this case, when there's no explanatory variables, it's just the mean value and their deviation from the mean. If you want to represent this in a matrix expression, at the top of this slide is the general latent variable model in matrix notation. As the name suggests, the latent variable model is the equation that connects together all the latent variables in your model. It shows how you're hypothesizing that they're connected to each other. The nice thing about the general matrix expression at the above these individual vectors and matrices below it is that this holds for any number of latent variables that might be in your model. And here is just showing what that diagram would look like. The regression coefficients giving the effect of the latent variables on each other are here. These last part of this matrix, the bottom three rows here, these are all zero because these give the effects of other variables on the exogenous variables. And by definition, we said the exogenous variables are not influenced by any other variable. That's why these are all zero. L3, 4, and 5 are the exogenous variables. They're not influenced by any other variable. We take a look here, right? There's nothing predicting L3, 4, and 5. And that's why they have the zeros there. Here it is, just highlighting that matrix equation. This is pretty much repeating what I had said here. But there's another part to this diagram, right? So those last couple of slides, all I showed you is how the latent variables relate to each other. Well, that's at a very abstract level. That's only showing how these abstract ideas like behavior intention, attitude toward the particular behavior we're talking about, subjective norms, these are abstract concepts. If we really want to analyze them, we have to connect these abstract concepts to variables that are in our data set. And that's the task of the next part of the model, the measurement model. Notice the diagram is showing this. The diagram showing that behavior at time 2 is measured by these three indicators, and L2 influences these three. Other than the error terms, there's no other influences on them. So behavior intention has no influence on Z4, 5, and 6. And behavior at time 2 has no impact on Z1, 2, and 3. Here is the set of equations that capture the relationships in that path diagram. The linkage, this is how we can use the data in the data set, the variables in the data set, by linking them to the latent variables that are in our theories. Now, all of these equations have a very similar form. The main difference are what I referred to before as the scaling indicators. So Z1, if I go back to the diagram, Z1 is the scaling indicator of behavior intention. So it's treated a little differently. These alphas here, these are intercepts, measurement intercepts. And in the scaling indicator, we're assuming the intercept is 0. We're giving the latent variable the same 0 point as Z1. And rather than lambda 2, 1 for the scaling indicator, we set its indicator just to 1. There still is an error term, and that has to be present. But its intercept is 0, and its regression coefficient, or factor loading, if you will, is 1. You can view every one of these equations like little regression equations. So Z2 is a regression equation of what we would get for the second measure that's regressed on L1. There's going to be a regression intercept, and there's going to be a regression coefficient. The lambda 2 one's the regression coefficient. If you have seen factor analysis, you would call that regression coefficient a factor loading. But they're the same thing. A factor loading is a regression coefficient. And here is the error term for that Z2. And we have that same structure throughout. So the second equation, right? We had one equation, was the latent variable model. We had that equation in L as the dependent variable. The second equation for this general system is the measurement model, and it is given at the top of this slide. And not to give away too much here, this single equation is sufficient to encompass all of factor analysis models. So factor analysis is one part of this general structure. It's just the measurement model. There can be any number of indicators or measures. There can be one or more latent variables influencing the Z. I showed you a diagram which was fairly clean, where each measure only related to one latent variable. But there's absolutely no reason why we couldn't have a diagram where there was more than one latent variable influencing individual measures. This is just repeating what I said on the scaling indicator. You select what you think to be the best indicator, set its intercept to 0, set its factor loading to 1. You can have correlated errors. So if you have reason to think that there's perhaps similar wording on some of the indicators that you're trying to use as measures, that would create an additional association between those indicators that's different than their common dependence on the latent variable you're trying to measure, you can put that in and test it. You can see if that makes sense. All that's here is just the summary form, and this is it. This is the model notation. There's two equations to it. One for the latent variables, one to relate the observed variables to the latent variables. This is just a batch of regression coefficients giving the latent variables impact on each other. This is a stack, a vector of regression intercepts. These are all the other influences on this L that aren't included in the model. If we go down to the measurement model, the Z, these are the measures, or the indicators just stacked in a vector. There's a regression intercept for every one of the measures. If it's a scaling indicator, that'll be set to 0, but for the other ones, we'll estimate it. The factor loading matrix, lambda here, I said that you could consider this a matrix of regression coefficients. Quite true here, or you can call them factor loadings if you prefer. These latent variables you could just name as factors. If you're from the factor analysis tradition, just call them factors. And then finally, all the other influences on these measures that are not included already in the model through the L matrix vector are put into this error or disturbance term. As far as assumptions that we're making for the latent variable model, these are not that important. These are just giving you the dimensions of those different matrices. But we have a regression-like assumption here. You know, we're assuming that the mean of all these omitted characteristics is 0. So that's a lot like regression. For the measurement model, we're again assuming the mean of these errors for the measurement equation. We're assuming that mean also is 0. We're also assuming that this error term is uncorrelated with these explanatory variables. The explanatory variables are these factors or latent variables. So the covariance of epsilon z with Li is 0. This is again a regression-like assumption, assuming that the error term is uncorrelated with the explanatory variables. And then we're assuming that the errors from the measurement model and from the latent variable model are uncorrelated. Now, one other assumption here, perhaps I should emphasize. we are assuming that if you pulled the errors out of here, so this is the errors for every one of the latent variables, both the endogenous and the exogenous latent variables. If you took out the errors that only corresponded to the latent endogenous variables, those errors are uncorrelated with the exogenous latent variables. So the errors of the endogenous latent variables are uncorrelated with the exogenous latent variables. An analogous assumption is made in regression with the explanatory variables. So, two equations to the whole model. What about the data? Well, you can analyze raw data, and this is just like a regular matrix of all disease. You know, notice this is just going to be a disease. That's the only thing we have observed in our data set. The latent variables, we can't put them in our data set by definition. But there are a number of situations where you can get identical results, and all you need is just to analyze the covariance matrix, the sample covariance matrix of the observed variables. That's what this S stands for. And the sample mean of the observed variables. So you can do fairly complex analyses without even touching the raw data, you know, just by using the sample covariance matrix and the sample means. The main times where you would use raw data is when you have non-normal continuous variables and you want to take account of that non-normality. Another instance where you would use raw data is when you have missing data and you want to take advantage of the different ways you have of handling missing data with this structural equation modeling approach. And then the third instance is if you have categorical observed endogenous variables. So if you have categorical measures or categorical outcomes, this too would call for having raw data for your analysis. The covariance matrix and the means, these are most useful when you have continuous endogenous observed variables and you just want to use the maximum likelihood normal estimator. Then you could just use that. Just a little bit of further clarification of notation. Some of this has already appeared. Mu, I always will use for the mean of a variable. If you want to know what it's the mean of, just look at the subscript. So if you see a mu of L, this is the mean of the latent variable. Mu of Z, this is the mean of the observed variables. The covariance matrix always represented with the uppercase sigma. You want to know what's the covariance matrix of? Look at the subscripts. So this is the covariance matrix of the latent variables, sigma sub LL. Sigma sub ZZ, this is the covariance matrix of the observed variables. And then alpha is always going to be intercepts. And if you want to know the intercepts of what, look to the subscript. This is the intercepts of the latent variables. This is the intercepts of the observed variables. Epsilon is always going to be an error term, and we've already seen this. Look to the subscripts. Epsilon sub L, this is the error of latent variables. Epsilon sub Z, this is the error of observed variables. B gives regression coefficients. These are L to L, so latent variable to L, latent variable influences, and Z to L effects. If you have exogenous observed variables that are influencing the latent variable, you also can put that with a B coefficient. The lambda, these are also coefficients. They are factor loadings. They give the impact of the latent variable on their measures. Okay, so let's pause for a couple of questions that I made up and then just see if there's any others that you have at this point. What is the difference between the path diagram and the equations that represent the model? I answered this a little bit earlier. The path diagram is a picture of the system of equations. And it's really a matter of what people find easier to work with. And you can work with either the equations that were laid out or you can work with the path diagram. Do all path diagrams look the same? This is a good question because it can be a source of confusion. And the answer to this in brief is no, although they can look very similar. For example, there are some people using path diagrams that introduce a separate symbol for the variance of every exogenous variable and the variance of every error. It looks like a little headphone almost that they put on the variables. So sometimes you'll see that in an article or in a discussion of these models. Sometimes people omit the error term just to save space. You know, if you have a complicated model and there's so many variables in there, you have to use judgment. You know, at what point is the path diagram so complicated that it's losing its utility? And sometimes you can stretch it a little bit further by not showing things like the error term. Or as I say in this next bullet point, if you have a really complex model with lots of measures and lots of latent variables, I've seen, and sometimes I've done it, I'll just present the latent variable model. You know, this may be my primary focus in an article. So I'll just show you the path diagram for the latent variable models and just explain, you know, in the text or a footnote or at the bottom of the figure, that only the latent variable model is shown. Another source of confusion is that DAGs, you know, came on the scene a little bit sometime after, a lot of years after path diagrams. These are framed as non-parametric structural equation models. And as I said in part one, there are some similarities between them, but there are some differences. One that I mentioned is with DAGs, they're setting up the single-headed straight arrow represents non-parametric relationships rather than ones that are necessarily linear in the parameters. So it's a more general representation of possible relationships. I also said the curved two-headed arrow differs between DAGs and in path diagrams. Okay. Any questions? Anybody want to turn on the mic to ask a question? Or Ilya, are you seeing anything in the chat? I'm happy to give a minute if there's any questions. Okay, if not, let's move on then to the major steps in structural equation models. What steps you would take to implement these? I'm going to highlight 6 steps, and we'll go over each one of them with some examples. First step, specification, basically saying formulating a model. Second step are the model implied moments, so understanding what they are. And the moments we're going to look at are mean values and variances and covariances. Third, you want to make sure your model's identified. You want to make sure it's possible to find unique values for the various parameters you're trying to get at. Estimation talks about how to develop estimates of those parameters, regression coefficients, etc. And then test the model refers to diagnostics we have that provide us information on whether our model is a good match to the data that we're analyzing. And inevitably, well, occasionally it doesn't work out this way, but most of the time, you find that there's a need to re-specify your model. You have to modify it because your diagnostics for your model are pointing to possible problems in what you laid out there initially. Specification, what's involved with this? Well, you as the researcher, you have to say, what are the primary latent variables that you're studying? What are the hypotheses linking those latent variables to each other? Once you've formulated that set of relationships between the latent variables, the next question is, how can I measure it? You know, what measures do I have to work with? And how do those measures connect to the different latent variables? So it is demanding substantive knowledge from you. You know, if you're working in an area where you don't have substantive knowledge, and you're just trying to do this by yourself, you're going to be stuck, because this really demands that you formulate, make some hypotheses. You or somebody else, maybe if you're collaborating, you could do it. If you're collaborating with a substantive expert, then that expert could formulate what the latent variables are, what the relationships are, et cetera, et cetera. But it's really geared toward reflecting as best as you can what your knowledge is of the set of relationships between different latent variables with each other, and how those latent variables relate to measures. So you've got to formulate that. There are three major types of specifications. And this gets back to the point I made in part one of this overview. I said that structural equation models, one way you could view them is as a very general statistical model. And this is reflective of that, because a subtype of the general structural equation model that we showed you, that two equation system, are simultaneous equation models. And simultaneous equation models have been most studied in probably econometrics, to date. So econometric type models, where you have multiple dependent variables, but you are assuming that there's negligible measurement error, we can see how we can get that as a subtype of this more general latent variable structural equation model. A few slides back, I mentioned that factor analysis could be considered the special case of this general model. So that's another subtype of the model. And the third type combines features of both. That behavioral intention model that I showed you as an example is one that has this general latent variable structure, where it has the measurement model as well as the latent variable model as part of it. Now, we're going to mostly focus on observed variables that are continuous, but I would like to mention that you can have categorical endogenous variables in these models. So the simultaneous equation models, this is the first subtype, important subclass. This assumes we've got one indicator per latent variable and that there's no measurement error. So this, in essence, is what we're simplifying our measurement model to. Our measurement model had each observed variable with a regression intercept or a measurement intercept, factor loadings times latent variable plus error. If you're using the simultaneous equation models, you're assuming my observed variables are essentially the same as the latent variable. So here is the general expression that we had. Here was the general measurement model. And in simultaneous equation models, this measurement model is going to be modified so we constrain these intercepts to 0. And we constrain this factor loading matrix to an identity matrix, and we constrain these errors to 0. So essentially, we're just saying our observed latent variables are equal to one another. Now we're going to substitute in to the latent variable model. Here's the latent variable model. If we know that L is the same as Z, we can just replace L every place it appears with a Z. And so when we do that, we get now a single equation that can represent simultaneous equation models with this expression. This is very similar to a multiple regression equation, but it's more like having multivariate regression equations. There's separate equation for each outcome that we're studying. The other difference is that what is a dependent variable in one equation can appear as an explanatory variable in another. And when you have that type of situation, you then can take a look at mediated effects. And there's a vast literature on mediation, direct, indirect, and total effects in the structural equation modeling literature, with very general expressions for how to find specific indirect effects, total indirect effects, etc. It goes way back, goes back decades. Here is a very simple simultaneous equation model where we have mother's education, father's education, determining a respondent's education, and then this respondent's education determines the occupation and the prestige of the occupation that this person gets. So we've got two endogenous variables, Z3 and Z4, and the impact of mother's and father's education on occupational prestige is shown as being totally mediated through the education of the respondent. This is just showing you the covariance matrix of the errors. Because these two errors are not correlated, that's why this entry is 0. These other entries are 0 here because we're assuming that the errors of the endogenous variables are uncorrelated with the exogenous variables. Here's the second major type of structural equation model, confirmatory factor analysis. All we need to do is grab the measurement model from the two equation system. We'll do it. That will take care of everything. Z is just the vector of all our measures or indicators, or whatever you want to call them, observed variables. Here are measurement intercepts. Here are factor loadings. Here are the factors or the latent variables. Here are the errors, disturbances, or in the factor analysis literature, these are sometimes called unique factors. We have the covariance matrix of these factors, sigma LL, and with the covariance matrix of the errors, sigma epsilon epsilon. This is an example of an article that colleagues and I did analyzing blood pressure. And in this data set, we have two latent variables, the systolic blood pressure and the diastolic blood pressure. In this data set that we analyzed, they had 3 measures taken for each person in the sample, fairly close to each other, in both the systolic and diastolic. So we're assuming that each of these indicators contains measurement error, and they're reflective of the true systolic blood pressure. So if we could remove all the measurement error from the systolic blood pressure, this is what we'd be left with, the systolic blood pressure here. Same thing with the diastolic blood pressure. Now, we have these curved two-headed arrows here, and the reason we include these is that the systolic blood pressure at time 1 was taken at the same time as the diastolic blood pressure at time 1. So if there's some systematic error that's occurring in time 1 measurement, we expect it to be shared among these two measures taken at the same time. And in fact, when we test that, we do find there is significant positive covariance among those two different readings errors that correspond to the time of measurement. So, there's something that you can just test on your own. You can, if you hypothesize something like that, this gives you the capability of just entering it into the model and seeing if it seems to occur, seems to hold. This is the general latent variable model, which is the third type, and this is just repeating the two equations we had. And here's an example, a different example than that behavioral intention one. In this one, we're looking at countries as the unit of analysis, and we are interested in industrialization of countries. Right? That's a fairly abstract latent variable, the industrialization of the countries. And even more abstract is the political democracy of the country. That's what D1 is in 1960, and D2 is in 1965. So the theoretical hypothesis that's being looked at here is the impact of industrialization on democracy at this first wave of data and democracy at this second wave of data. And for the second wave of data, we're also controlling for prior levels of democracy. So you can find in literatures in political science, political sociology, some economics, discussion of how industrialization is related to democracy. That's fairly abstract theoretical ideas, and it is represented in this latent variable model. But we need indicators from a data set to enable us to be able to test this. And so there's 3 indicators of industrialization, and there's 4 indicators of democracy at 2 points in time. So what is going on with these curved 2-headed arrows for the democracy indicators is that since Y1 is the same as Y5, if there's some error in Y1, it's likely to be associated with the error in Y5. So I want to control for that. That same type of argument holds for the error in Y2, 3, and 4 with their corresponding Y6, 7, and 8. So this is an example of a model that's allowing us to test those hypotheses that are fairly abstract, controlling for measurement error and controlling for correlated measurement errors that are likely in a data set like this. So that's specification. I mean, that's what that looks like. And I just showed you several different examples from, quite different areas of research. The second step are the model implied moments. Now, I don't expect you to, get all the details on this, but I'm trying to give you a sense of what's involved in this modeling. And to do so, I need to define a couple of terms. The simplest terms to define are the population covariance matrix of the observed variables. That's what sigma is, the population covariance matrix of observed variables. So these are the z's, and we're just taking their covariance matrix. The mu stands for the population means of the observed variables. And so this is what they would be in the population. This theta, this is a vector that contains all of the parameters that are in the model that you formulated. So the composition of theta will depend on which one of these models you're using. So theta could contain regression coefficients, it could contain factor loadings, it could contain variances of errors, covariances of errors, variance of exogenous variables, covariances of exogenous variables, whatever is present in your model. That's what this theta is.
Ken, there's a question, I think, on a few slides back about why we correlate specific errors.
Sure. Do you want to ask it, or is it typed out, or?
It's typed out, yeah.
Go ahead. So which, was
why
it
are Y2 and Y4?
Yes. Sharp eye and great question. Y2 and Y4 came from, these are subjective ratings. And Y2 and Y4 came from the same judge. So the logic of including the error of Y2 and the error of Y4 is that if this judge made an error in Y2, and it was a he probably made a similar type of error in Y4. So I'm trying to allow for errors being correlated because the rating comes from the same judge. The other measures come from different judges. And that's why I didn't correlate them. And so 6 and 8 are also correlated for that same reason. That's the same judge who did Y6 and Y8. And I don't want my analysis to be distorted by any biases that this judge might have had when he did these ratings. I want the control for that. Anything else on that? Okay. So what this hypothesis is saying, fundamental hypothesis, it's saying that there exists a nonlinear function of those parameters in your model. All those regression coefficients, variances, covariances, factor loads, there's a nonlinear function of them that you can put together. And if your model is correct, you'll be able to exactly predict the population covariance of the observed variables, covariance matrix of the observed variables. It's saying those same parameters, another nonlinear function of them, if you mix them together, they're going to exactly predict the mean value of the observed variables. So this is a very strong hypothesis. It's saying you got an exact prediction of both the mean vector and the population covariance matrix of the observed variables based on your model structure. And that null hypothesis will be true if your model's true. So that's what these implied moment matrices are about. There's only two moments we're looking at. We're looking at the means as the first moment and the covariance matrix as the second moment, and we're matching them together. Each time you formulate a model, you will formulate a different sigma of theta and mu of theta. So it's the model that dictates what that nonlinear form of theta is for sigma and that nonlinear form for mu. So it's dependent on your model structure. Let me try to illustrate this a little bit more with a factor analysis model. Here we have a single factor and we have 4 indicators, Z1 through Z4. We're scaling this to Z1, that's why that 1 appeared there, and we have 3 remaining factor loadings, and we have an error for each of these observed variables. This is what the population covariance matrix looks like for that 4 indicator factor analysis model. We've got the variance of each of the indicators, then all possible covariances of those indicators. That's the sigma in that expression. That's sigma equals sigma of theta. That's what sigma looks like. Now the sigma of theta, there's a formula to predict what the sigma of theta, or to tell you what the sigma of theta will be for any model you can come up with, any of the models in our classes. And that formula was applied here. And this is telling you which model parameters are predicting which variances and covariances. Just to give you a sense of how this works. If this model structure is true, then the variance of Z1, the variance of the scaling indicator, should exactly equal the variance of the factor or latent variable plus the variance of its error. If this model is exactly true, just to give you another example, the covariance of Z4, Z1, that will equal the factor loading for the 4th indicator times the variance of the latent variable. And so it goes for every element here. Here are the model parameters and nonlinear function of them. They should exactly predict the covariances and variances of the observed variables when your model is true. This is just giving you for the population mean of the observed variables. Here's the nonlinear function. Again, there's a general matrix expression for this, and I just plugged it in to get these numbers. This is telling you the nonlinear functions that you can have to exactly predict the mean of each observed variable. As an illustration, the mean of the 3rd indicator, if my model's true, that should equal my measurement intercept for the 3rd indicator plus the factor loading for the 3rd indicator times the mean of the latent variable. I should be able to exactly predict this mean right there. So those are the model implied moments. And they appear in identification, estimation, and test of the model. So they play a pretty central role in these models in several different steps that we're going over. Let's then go to identification, unless there's some other question that's... Any other questions, Ilya? Okay. This identification is a tricky issue to understand, and we're not going to be able to go over it in great depth, but I want to give you at least an intuitive feel for it. In part 1, I said that we can't just let the data tell us what's going on with a set of variables, in that if we allow every variable to influence every other variable, all the errors to correlate, that's an under-identified model. And what under-identification means is it's not possible to find the unique values, the real coefficients, even if we had population information. And to try to give you a little bit of a feel for this, let's suppose that our implied covariance matrix here was extremely simple. We had just Z1, we had one variable. So we had the variance of Z1, and we're told that equals theta1 plus theta2. If this is the only information we have to work with, even if I give you the population variance of Z1, I tell you it's 10, you still can't tell me what theta1 and theta2 are. It could be it's 5 and 5, could be 7 and 3, 9 and 1, 11 and minus 1. There's an infinite number of values that would be consistent with this relationship. Theta1 and theta2 are under-identified. So it concerns, can we even find unique values? This is an issue that you don't see in something like multiple regression, because in multiple regression, it's built on assumptions that force it to be identified. You know, if you ever wondered about why do we assume that the error term is uncorrelated with our explanatory variables if we're doing ordinary least squares regression? Well, if we allowed that error term to correlate with our explanatory variable, it would be under-identified. We couldn't get our regression coefficients, even if we had population information on the y variable and all of the x's. So the reason you're not seeing this issue come up in multiple regression is that the assumptions for multiple regression are set up so it's exactly identified. In simultaneous equation models, where you start having multiple dependent variables, then this becomes more of an issue. In factor analysis, it's also an issue, and in the general model, it's an issue. Now, the most brutal way to try to attack this is to use this model implied relationships we talked about, sigma equals sigma of theta, mu equals mu of theta, and try to solve for the parameters in terms of mu and sigma. So solving those equations can be quite messy if you have a decent sized model. More practical are identification rules. These are worked out rules that are easier to apply that sometimes can tell us whether our model is under-identified or identified. And finally, there's empirical tests that give us indirect evidence on identification of the model. This 4-indicator single factor model that we're dealing with, we really don't have to solve out all these equations because there's a general proof called the 3-indicator rule that says if you have at least 3 indicators of a factor, and there's no correlated errors, that factor is identified. So you can just use that rule, look at this picture, and know you've got an identified model. And there are many other identification rules that you could apply in factor analysis or in simultaneous equation models. This is a point I can stop at to see if there's any questions before I go on to how to estimate these models. Okay, I'll go on to estimation then. Here is that same null hypothesis we've seen a few times now, sigma equals sigma of theta, mu equals mu of theta. We're predicting the population covariance matrix of the observed variables and the population mean vector of the observed variables. Based on maximum likelihood estimation principles, this is an expression that we're trying to minimize in order to develop the estimates of all the parameters in the model. Now, I know this looks extremely messy if you haven't seen it before, but all of this boils down to a single number, and we're trying to make this number as small as possible. So we're trying to plug in values of our model parameters, both here and there, and multiplying them in these various functions times the sample covariance matrix or the sample means to try to make this number, try to choose values to make this number as small as we can. And the estimation proceeds in that way. There's not a nice, neat equation that we can write out and say theta hat's equal to such and such. You need numerical minimization procedures. People who are listening to this, I'm sure you've seen things, you've used logistic regression, you've used other procedures that require numerical minimization, and that's what's required here as well for this maximum likelihood estimator. This was originally derived assuming multivariate normality, but there have since been analytical work that has justified this estimator under slightly looser assumptions. For example, you can still use this estimator and have nice significance tests if you have observed variables that do not have multivariate kurtosis different than the normal distribution. So you can have skewness as long as that skewness is not accompanied by multivariate kurtosis. Another assumption is that the error terms, the errors in those equations, are independent of the exogenous variables. This is another justification for this fitting function. Even if they don't work, there's lots of other options we have. For example, if you have non-normality and you have excess multivariate kurtosis, there are corrected standard errors in test statistics that you can apply that take that into account, or there's bootstrapping approaches that can handle that. Now, one issue that is not taken care of by these distributional problems and distributional corrections is that this is a full information estimator. And what that means is that every parameter in this model, everything, all the equations, are estimated simultaneously. And when it does that, it is borrowing information from different parts of the system to develop the estimates you're interested in. The problem with that is that if there is a flaw in one part of the system, that could contaminate even perfectly fine parts in other equations in that model. So there's potential of spreading error from one part of the system into another part of the system. That's a disadvantage of this full information approach, full information maximum likelihood. A contrast to the full information are limited information estimators. And as that name suggests, it doesn't estimate the whole system at once. In fact, the most common way of doing this in structural equation models is to estimate single equations. So rather than all the equations at once, you're taking one equation at a time. And the trick behind doing that, I'll try to give you a little bit of an intuitive feel for it. Here are the original equations we had, two of them, a latent variable model and a measurement model. I said that each latent variable needs to have a scale assigned to it, and those are the scaling indicators. Well, it turns out we can write the latent variables as equal to the scaling indicators minus their error terms. And when we do that, we can go back to these two equations, and every place that L appears, we can replace it with the scaling indicator minus its error term. And the result is these two equations now are transformed into equations that have just observed variables. So this is a latent to observed variable transformation. So you're actually eliminating the latent variables from the system. And you're getting a bunch of equations that look like regression equations with only observed variables. And we can take each one of these equations, estimate them one at a time. The main difficulty that arises from this transformation is we now have a more complex error term that will correlate with some of the right-hand side variables. And to take care of that, we use instrumental variables. If you haven't seen instrumental variables, let me just, in a nutshell, let me just tell you that what they do is they are a way of providing estimates of coefficients and intercepts in an equation when some of the right-hand side variables correlate with the equation error. And they're variables that are not necessarily in that equation, but could be elsewhere in the system, and you use them to develop estimates of all your coefficients. These instrumental variables, in typical treatment of them. So if you read about instrumental variables in econometrics or in other social science ones, often the way they're presented is that these are variables that you get from outside your system of equations. So you look for variables that can serve as instruments. The approach that I'm discussing here, this model implied instrumental variable, what it does is it looks among the observed variables already in your system, and it determines which variables in my system already could I use as instruments, because according to my model, they do not correlate with the error for that particular equation. So again, that's why they're called model implied instrumental variables. Again, we're dealing with one equation at a time. We have algorithms to determine what are the model implied instrumental variables for every equation in the system. And we can collect together all the instruments for a given equation in a matrix we'll call V. So this V contains the model implied instrumental variables for an equation. Here is a single equation. Looks just like a regression equation where we have y as the dependent variable. It's a vector containing all values of the dependent variable. U is a matrix containing all the explanatory variables for this one equation. Beta contains the corresponding coefficients for each variable, and E contains all of the errors in this equation. So to get the regression coefficients and intercepts, with this MIV two-stage least squares approach that goes equation by equation, we do not need numerical minimization. We have this matrix expression here, which if we plug in the values of the observed variables, the output will be our factor loadings, our regression coefficients, whatever is present in that equation. So this is a contrast to the full information in at least two ways. We're just taking a single equation rather than estimating the whole system. And rather than numerical minimization, as was true for full information, we have an explicit expression, non-iterative, that we can use to develop those coefficients. Couple of the properties of it. This is asymptotic distribution free, so we don't have to assume normality. It's consistent, asymptotic, unbiased. There's standard errors and significance tests readily available. And here's perhaps the main advantage. When you do one equation at a time, rather than estimating the whole system, you have greater robustness to errors in your model specification. So you formulate the model, and you, in all likelihood, are making some mistakes. What this estimator does is it's better at isolating the mistakes in other equations and preventing them from entering the particular equation that you're estimating. So it's more robust to those structural misspecifications. Right, so that's estimation, sort of a broad sweep of what it looks like. And I just gave you a full information, a limited information. There are actually about a half dozen or more other estimators that are in this field that will appear every so often. It looks like I'm not seeing another question in the chat. Is that right, Ilya? Yeah, okay. All right, how do we test these things? All right, so we've specified the model. We've established that it's identified. We've estimated the model. Now, how do we know that what we've specified is correct? Well, fortunately, we have some diagnostics that'll give us information on whether there's a suggestion of problems in our model or whether there seems to be a good match between our model and the data. These I want to separate into the full information type of test versus the limited information. So the first one I'm going to consider is the full information estimator, the maximum likelihood that we talked about. It has, as I said earlier, this null hypothesis sigma equals sigma of theta, mu equals mu of theta. This will hold if my model is true. Right? This null hypothesis holds if my model is true. Fortunately, we have a chi-square test of this null hypothesis. A few slides back, I gave you that complicated fit function. Well, if you take that fit function at its minimum, multiply it times n minus 1, you'll get a test statistic that in big samples follows a chi-square distribution. And the null hypothesis of this is that evaluated based on that chi-square test statistic with degrees of freedom that are given here. In addition to that chi-square test, there are other fit indices that appear in this literature. I've just listed a few here. I don't have time to go over them in detail. I will tell you that most of these fit indices, the top 2 fit indices, have a maximum of 1. So the closer to 1 you are, the better the fit. This one, the closer to 0 you are, the better the fit. The BIC, which you've seen in other contexts, I'm sure, this one, the more negative the value, the better the fit. So these are other ways of measuring fit that are not based just on the significance test for the chi-square. In the limited information estimators, rather than testing the whole system, that's sigma equals sigma of theta and mu equals mu of theta, what we have here is a test of each equation. So this is a Sargon test. This was developed in econometrics in 1958. And we can form this rather simply. And it is a test as to whether the instrumental variables we used for our equation appear to be uncorrelated with the equation error term. Now, by carrying out this test, we are actually testing our model structure. And the reason I say that is we got these model implied instrumental variables, these MIVs, M-I-I-V-S. We got these MIVs based on the structure of our model. So if we reject the MIVs, we're rejecting our model because they were the ones that led us to those MIVs. So this helps us to pinpoint problems by looking at each equation and see whether it passed or not. If our model were valid, all the MIVs would be good. Now, is there one other question?
Yeah, Ken, there's a question that I suggest that the person might want to ask it aloud.
Sure.
Maybe give a moment for that.
Sure thing.
Hi, sure. I was wondering if the choice of the type of SEM that you're using, does that guide your choice of the estimator, or you know, are you just sort of free to use any of the 3 types and then any estimator, depending on your theory and data structure?
Yeah, that's a great question. So the ones I'm talking about, the maximum likelihood and the MIV two-stage least squares, they're assuming your endogenous variables are continuous or decent approximations to continuous. So if you had categorical variables, you know, maybe dichotomous outcomes, that sort of thing, there'd be different estimators that you would want to use. But if your outcome is continuous, you could use either the maximum likelihood, which is the most widely available, or the MIV two-stage least squares. Now, the MIV two-stage least squares is asymptotic in large samples distribution free, but we do have corrections for non-normality with the maximum likelihood. So in that sense, they're quite similar. Does that answer your question?
Yeah, I think so.
Okay.
Thank you.
Sure. Any others? I see there's a few more chats since the last time we stopped, but okay. So let's go back to this nice, simple 4 indicator example. This example is coming from the area of environmental studies. The latent variable is subjective air quality. And there's 4 different indicators of subjective air quality, subjective indicators. This is the overall air quality. This is the color of the air, the clarity of the air, and this is the odor of the air. So what is being tested here, does it make sense to think that people formulate an opinion on the quality of the air, and then this drives the response to all 4 of those questions? And what we can see when I apply the maximum likelihood estimator here, this is statistically significant. Generally, we like statistical significance, but in this context, this is saying we're going to reject the null hypothesis. And the null hypothesis is that sigma equals sigma theta, mu equals mu theta. In other words, our model is correct in dictating how to predict the covariances, variances, and means of the observed variables. So this is evidence against our model, right? So that's what that's telling us. Now we said there's another way of testing this with the mid 2-stage least squares. So for this same example, I've done this Sargon test. And this is kind of interesting. You can see the clarity question fails quite easily at 0.0001. So this is telling us there's a problem with these 2 instruments, color and odor. Your model said that color and odor should be good instruments for this equation. This highly significant Sargon test tells me that one or both these variables are problematic. Color also fails this test. Odor is sort of scraping by, so it's not as strong evidence as we find for the clarity and color. So you can see you're kind of getting different information here. One is kind of the test of the whole model, and here's a test of each equation of the model. This leads us to re-specification. You know, we are in a situation with that air quality example, subjective air quality, where we are rejecting aspects of our model no matter which estimator we use. Now, how do we reformulate the model? Well, I would, in general, put my money on substantive-based revisions. You know, again, this calls for expertise, substantive expertise, to try to get some sense of how we could reformulate the model. But there are other empirical techniques that are used in practice. One is a Lagrangian multiplier test. This is sometimes called the modification index. It tells you how much the chi-square fit would go down for the full information estimator, how much the chi-square fit would go down if you entered a parameter into the model, a previously restricted parameter to 0. If you entered it, what would happen to that chi-square? The Wald test shows you what would happen if you constrained some non-zero estimates to 0. And then there's residuals also that you could look at. Now for this, this particular problem, I knew the person who collected the data, and a guy named Greg Cermak, psychologist, and he told me that people had trouble distinguishing the color and the clarity question from each other. So they were asked to rate the color and clarity of the air in a particular scene. And they said, well, what's the difference between those 2 questions? And he didn't give them any directions. So it seemed logical that there might be correlated error between these 2. And indeed, when we do that, we can see this chi-square goes way down. You could argue it's still statistically significant at the 0.05, but there's a substantial drop in it when we introduce that. And this is a positive association supporting that hypothesis. So again, to repeat, these are the major steps: specification of the model, just saying what the structure should be, knowing what the model implied moments are. Fortunately, this is all programmed into the computer packages, so you don't have to set that up. It's built into the estimation routines. Identification, rules of identification are out there that can help you with it. Estimation, we have a choice of several different estimators depending on the nature of our data and the model. We have tests of the model, which can give us feedback on whether the specification we set up really is consistent with the data. And we really would want this. I mean, it would be terrible if whatever we said worked. So this is a kind of check on us in terms of whether we're doing something that's at least plausible given the data we have. And then re-specification, which really enters the more exploratory realm, and you have to keep that in mind as you're assessing your re-specified models. Now, software. Let's talk about that. This is just a sample of the packages that are available. There's a ton of them. Probably today, I would say the most popular, probably M+ and Levon. Both are, excellent packages. Literal is still quite popular. This new SEM procedure in JUMP in SAS. This has some quite interesting features too. GLAM in Stata. There's a SEM procedure and GSEM in Stata. So there's lots of ways you can gain access to these SEM packages. And the asterisk means that these are free softwares. So you can see a few of them are actually free. Here's a coding example. This is that industrialization democracy example I had when I was illustrating the specifications. All I'm giving here are the indicators of industrialization, so GNP per capita, energy per capita, percent labor in industry, and then these are the measures of freedom of the press. The latent variables here, I1 is industrialization, D1 is political democracy, D2 is political democracy at the later point in time. This is just the path diagram to remind you of the model that we're estimating. So what I'm about to show you is what would the coding look like if we did this in Levon. There's the picture. Here's the code. So this again is an R package. We're naming the model demint. You can call it whatever you want. This is how we specify the measurement model. So this says industrialization is measured by X1, X2, X3. Democracy at the first wave is measured by Y1, 2, 3, and 4. And democracy at wave 2 is measured by Y5, 6, 7, and 8. Then this is giving us the latent variable structure. This is saying that regress democracy in that first wave on industrialization on the first wave. And this is saying regress democracy at the second wave on industrialization of the first wave and democracy of the first wave. So these are kind of giving the regression commands. These are giving kind of the measurement commands. And these double tildes, these are telling us correlations or covariant. When I was reviewing that article, I told you that we use the same measures at two points in time, and that gives us reason to suspect that some of the errors might be correlated with each other. So that's what I'm doing here. I'm saying the error of Y1 correlates with the error of Y5. The error of Y2 correlates with the error of Y4 and Y6, etc. This is how we get the mean value for industrialization and the regression intercepts for democracy in that first equation and the second wave democracy here. This is how we tell it the scaling indicators. We're saying make X1 the scaling indicator of industrialization, make Y1 the scaling indicator of democracy at the first wave, and make Y5 the scaling indicator of democracy at the second wave. So here are the commands on how to run it. So demint fit, so this is where you're going to put the fit. Use the, this was using the SEM procedure, model equals demint data. This tells you where the data is. Estimate the mean structure. If there's any missing data, this is a missing value routine. And it says use the maximum likelihood estimator. And this is how you get the summary statistics from it. And so here are the summary statistics for that model. And this is telling us whether there's evidence against the model or not. Remember, it's this odd situation where not rejecting the null hypothesis is support of consistency between your model and the data. So we're not rejecting it at the 0.329. So we don't have any evidence to say that there's some real flaw here. These are some of the other fit indices we talked about. I just briefly mentioned. So those are all diagnostics on the overall model with the maximum likelihood estimator. Here is the latent variable equation. So we're going to get the impact of industrialization on democracy at that first wave. We got a standard error, a z-value, a p-value. We have a standardized coefficient. And this is democracy at the second wave, regressed on democracy at the first wave and industrialization. So we got that output. Here is the measurement model. So this is telling how each indicator relates to the latent variables. These are factor loadings, if you will. And we have standard errors and p-values, et cetera, for them. Here's something you're less used to probably seeing, but this is giving us variances. So these are error variances of the indicator. So the error variance in X1 is 0.082. The error variance of X2 is 0.10. And we have significance tests of those error variances. Here is the variance of the industrialization, and here's the error variance for the democracy first wave equation and for the democracy second wave equation. And here are those covariances, which we hypothesized that there might be present for some of the errors. Not all of these error covariances are significant, but some of them are. And here are R squares. You get a series of R squares for this. So you get R squares for the measures. So what this X1 is saying is that 85% of its variance is explained by the latent industrialization variable. And this one's saying that 95% of X2's variance is explained by the latent industrialization variable. We also have R squares for the latent variable model. So here we have 20% of the variance in the first wave of democracy is explained by industrialization, the only explanatory variable. And here with D2, where we have the lag D1, almost 96%, over 96% of the variance is explained. So you get a lot of output and a lot of interesting results here. This is the Mifsum. So we said another estimator is the MIV two-stage least squares estimator. This is code that was locally written by Zach Fisher, who's a postdoc at the Carolina Population Center. And here it's set up so it has a very similar structure to Levon, which we just went over. So these equations are going to look the same. But here's what we're going to do to get the output. We use this MIV-E, and it tells us what the model is, where the data come from, and then summary statistics. And here's the output, and you'll see the coefficients will differ a little bit, but they're generally fairly close. But here's what's different. With the MIV two-stage least squares, we get a chi-square fit for every equation. So we can see how each equation fits. And we did find with that maximum likelihood that we had a good fitting model overall. This good fit of the model is reinforced by the fact that none of these Sargon test statistics are statistically significant. So the model implied instrumental variables that were suggested by the model seem to work out. There's no evidence to contradict them. All right, so is there any question on that before I conclude? Okay. So, I tried to give you a broad overview of structural equation models, and it has many functions, many desirable features. It is a powerful way to test your causal assumptions. You can't prove them, but you can reject them. It turned out in that last example, we weren't able to reject them, but that doesn't mean they're true. It may be another test of them in a different population, different time period, they are rejected. It also is a very general statistical model. By imposing the assumption of no measurement error, we can get simultaneous equation models. It's just one part of it. Or if we want to do factor analysis, we have a separate equation from the measurement model that could be used for that purpose. And most intriguing is that you can incorporate these abstract latent variables that appear in many theories, many hypotheses, or even concrete variables that are poorly measured and you want to take account of that measurement error. And when you have multiple measures of it, you can do that, and you can control for your test of hypotheses, holding the measurement error constant. If there's confounders and suppressors, and as long as they're part of the model and you're estimating the whole system, they should be taken care of. We didn't go over it in much detail, but there's lots of options for remediation analysis with this. A lot of it programmed up into some of the packages. Whole bunch of diagnostics and test the models that aren't available in other approaches. And also, you can reveal some counterintuitive relations that really aren't visible when you just look at bivariate or single equation approaches. And fortunately, there's lots of software packages out there that enable you to do this. I don't think there's good excuses now for not taking account of measurement error in so many of the models that we're estimating. It's not a software limitation. We've got that out there. So that can be done. And I also should say that I just really scratched the surface here. There's all sorts of other extensions to structural equation models. There's some fascinating multi-level structural equation models that give you incredible flexibility when there's different levels of analysis. I mentioned in answer to a question in part 1 that there's just an incredibly wide variety of longitudinal models that could be fit, and you can put them in a similar framework so you can actually compare different longitudinal models. So you could compare like a growth curve model to a fixed effect model and see which seems to have the best fit. I mentioned, but didn't really go into any depth on categorical variable models, where you can take account of the categorical nature of some of your endogenous variables in the analysis. There's a lot of studies on robustness, which I didn't talk about. Colleagues and I have been working out robustness conditions for that MIV two-stage least squares, and we found some really incredible results that I think could be quite useful if you're trying to see when one part of the system could affect another part of the system or not. There's books on Bayesian structural equation modeling, so lots of Bayesian approaches to data like this. There's latent class models combined with structural equation models, where if you're not sure about, you think that there are underlying groups in your set of models, but you're not quite sure what those groups are, you can simultaneously estimate your structural equation model, but also the number of latent groups that might underlie those data. In the situation where you have actual group membership and you know the group membership, there's just great tests of seeing whether the same relationships, whether they're measurement relationships or latent variable relationships, hold across these different groups. And there's all sorts of mediation analysis that can simplify fairly complex tasks. So that's what I have to say, but I'd be happy to stick around another couple minutes if there are some questions on what I've gone over. You can just open up your mic or let Ilya know on the chat and you're about to open your mic. And I thank all of you who came to this one or the other one, and hope to see you around. Bye-bye.